pleasure to you know, give a talk in front of all of you. So today I'll be telling you about some developments that we've made in the past couple of years about quantum aspects of black holes. And a lot of these developments were driven here at Berkeley by a great group of postdocs, graduate students, and undergrads who I had the pleasure to work with. So throughout the talk, some of these faces will appear again, just because I want to see them slightly embarrassed. So let me start with the way in which I think about black holes. So I always viewed black holes as a sort of Rorschach test for the level of approximation with which different theoretical physicists view the world. So suppose that as a physicist, you're asked to describe a black hole when left in isolation. So let's say that you're a general relativist. What you would say is that if you're a general relativist, you would view the black hole as a purely classical object. It is nevertheless a very interesting object because it has an event horizon, a surface in space past which we cannot escape. While this object is very interesting, the event horizon makes these objects ridiculously simple. And this is because of a theorem known as the no-hair theorem. According to the no-hair theorem of general relativity, a black hole is just described by three parameters: its mass, its charges, and its angular momentum. These parameters fully specify the geometry of space and time. And because of this property, the black hole is a stationary solution in which these three parameters just stay constant forever, since nothing from behind the black hole horizon can ever escape. So it's a fixed geometry forever, interesting to study, but a little bit boring at the end of the day. Now, suppose that you ask the same question not to a general relativist, but to a particle theorist. So the particle theorist is obviously interested in particles. So he would take the black hole and try to see how the particles that we know about in our own universe would behave like on this black hole background. So they would consider the standard model, which is a quantum field theory, coupled to the curved geometry of the black hole. And the particle theorists will find that excitations of fields created outside of the black hole horizon here can potentially escape to infinity, while all excitations created behind the black hole horizon are stuck behind the horizon forever. And because of this discrepancy, an observer far away from the black hole, let's say that this is Q here at infinity, an observer far away from the black hole will see a flux of particles being emitted from the black hole, even if the black hole is in the vacuum state. And because the disparity between the modes inside and the modes outside has to do with the very short-range behavior of the particles that we know in our own universe, and this short-range behavior is universal, at infinity, the emitted flux will also have universal properties. So an observer at infinity will actually see that the flux that the black hole emits is a perfectly thermal flux. It's like the black hole, when you look at it from far away, looks like an ideal black body in our own universe, at least seemingly. So the black hole can be viewed as a thermodynamic object with temperature T. Now, any object that has a temperature, here is an example of what the temperature is for a black hole for which the charges and angular momenta are zero. That's known as a Schwarzschild black hole. And here is just the formula for the temperature. Then any object that has a temperature also has an entropy. And this observation leads to one of the most profound formulas in physics, the one that I wrote here, which is known as Hawking's entropy formula. And Hawking's entropy formula tells us that regardless of what black hole you look at, regardless of what fields exist and what particles exist in our own universe, this entropy of black holes is universal and is always proportional to the area of their horizon. Now, the reason why I love this formula is because it involves all aspects of theoretical physics, which can be seen from the presence of all fundamental constants. It involves thermodynamics through the presence of the Boltzmann constant. It involves relativity. Well, we're working in the theory of general relativity, so of course you'd expect the speed of light to appear. It involves gravity through the presence of G Newton. And moreover, it involves quantum mechanics through the presence of H bar. So this formula combines all the fundamental constant to give you a dimensionless number, which is the entropy of the black hole. And this formula brings me to the way in which I and many other quantum gravity theorists answer the Rorschach test of a black hole. We want to describe the black hole not as a macroscopic object, but rather we want to understand it at a microscopic level by allowing the geometry of space and time itself to fluctuate. And Hawking's entropy formula is a useful guide towards that. And the reason why it's a useful guide comes from the early days of quantum mechanics. In the early days of quantum mechanics, Gibbs, Planck, Jeans, and many others used the thermodynamic properties of gases to infer something about their microscopic structure, right? And that's our goal today. We too will want to use the thermodynamic properties of black holes to understand their macroscopic structure. So concretely, how we can do this is that an entropy should always capture a coarse-grained approximation for the count over the actual possible quantum states of black holes. So you might be used from your first StatMech course to the formula that the entropy of an object is kb times the logarithm of the possible number of states of that object. And in quantum mechanics, these are the actual quantum levels of the system that we're studying. This would be like the possible energy levels of the black hole. Now, since black holes are purely gravitational objects, understanding the quantized states of the black hole is akin to understanding quantum gravity itself. So our goal for today is to try to understand in as much detail as possible how this entropy actually captures the logarithm over a number of states. And this is what I'm excited to tell you about today. Just like Planck pushed thermodynamics quantities to their extreme in order to understand the microscopic structure of gases, we too will probe Hawking formula at its breaking points in this talk to understand the microscopic structure of black holes by using quantum gravity effects. And throughout the talk will have 3 parts, and throughout the 3 parts, the first part will talk about how quantum gravity modifies the statistical mechanics of the black hole. Part 2 will talk about how quantum gravity affects the radiation or the thermodynamic, the radiation that a black hole emits and its thermodynamics. And part 3 will show you how quantum gravity effects can even be sufficiently strong to cause the black hole spectrum to become discrete. For all these 3 parts, you will see that the analogy I was making with the early days of quantum mechanics is a bit more than a coincidence. So along the way, we will find many phenomena that parallel those found in the early days of atomic physics. And because I had students that were in my quantum mechanics class over here, I'll ask them to judge in the end whether they encountered the phenomena that we discussed in class. Great. So with this in mind, let's ask a basic question. What is the extreme regime for Hawking's formula? When do we expect Hawking's entropy formula to fail? So one regime in which we expect it to fail is when the quantum field theory on curved space-time approximation that Hawking made in order to compute his entropy formula just doesn't make sense anymore. And this is a regime in which our theories of particles in our own universe cannot be trusted, namely the very high energy regime or very short distance regime. So if instead of looking at ordinary black holes, we look at very, very tiny black holes, these black holes would probe very high energies in the theory. So if you take a black hole whose size is roughly given by the Planck scale, if you look at it, the temperature of the particles that it emits, that temperature would also be of the order of the Planck mass. And in order to understand particles with Planck energies, you really do need a much more detailed theory for the particles that we know in our own universe, including how they interact with the gravitational force. And in this regime, the entropy of the black hole also becomes very small. So while this regime is tantalizing because it seems that we can understand the properties of individual black hole microstates, it's a bit out of reach. It's an incredibly hard limit to understand because it requires understanding the theories of particles and gravity in our own universe in extreme detail, which we cannot do yet. But stay tuned until the end of the talk when we'll come back to these regimes and we'll actually see that there are special cases in which we can understand this regime perfectly. Now, the other regime that was a bit out of sight for high energy theorists is the cold regime. So as many condensed matter physicists in this room would tell you, interesting physics can also be probed not only at very high energies, but also at very low temperatures. And lucky enough, we know plenty of examples of black holes in our universe that can be arbitrarily cold. Namely, if a black hole has a non-trivial charge, a non-zero charge or angular momentum, there's a regime where the mass can decrease to a finite number, keeping the temperature extremely small. And this is known as an extremal black hole. A very cold black hole is known as an extremal black hole. So what are extremal black holes? Well, we can start with a black hole of mass m and charge q. And for a second, let's ignore the angular momentum of the black hole. Let's just set that to 0. A black hole with an arbitrary mass and charge has spatial slices that are curved that roughly look like this. As you approach the horizon, the space looks more and more curved, and eventually past this surface, no information can escape outwards. Now, as we cool the black hole, the length of the space-time of the spatial slice close to the event horizon becomes longer and longer and longer, while the size of the spheres surrounding the horizon, these like circles that I drew around the black hole horizons are like spheres surrounding the black hole, while the size of the sphere remains finite. So you can end up in this way, if you start with an arbitrary charge q. In our own universe, you could end up with a black hole whose mass at extremality is exactly equal to its charge. Now, let's look on the right-hand side. There is a plot of the area of the black hole as a function of the temperature. What you can clearly deduce from this plot is that as the black hole becomes cooler and cooler, eventually the area of the black hole just goes to a constant, and that constant turns out to be pi times the charge square of the black hole. So it just goes to a constant. But we know that the area, according to Hawking's formula, is actually connected to the entropy of the black hole. This means that as you cool down the black hole more and more and more, the entropy actually goes to a constant. Now, if you think about it, this poses a little bit of a puzzle. It's a violation of the third law of thermodynamics. So if you take the entropy of the black hole, the exponential of the entropy of the black hole, at 0 temperature should capture the number of ground states that such a black hole has. So if you just take the area of the black hole to capture that entropy, then for instance, for a solar mass black hole, the degeneracy of ground states that the calculation would predict would be 10 to the 10 to the 76. This is just in an ordinary theory of gravity in our own universe that has like no special symmetries. It's as if I gave you a quantum system and you figured out a way to compute the ground state degeneracy in the quantum system, and you found out that as you increase like the charge or angular momentum in that quantum system, this degeneracy grew exponentially without having any symmetry principle to explain where this degeneracy comes from. So without a symmetry principle, this would violate the third law of thermodynamics. Now, even weirder things happen when you go to this cold limit. Instead of looking at the area as a function of the temperature, at the size of the black hole as a function of the temperature, people in general relativity can also compute the mass as a function of the temperature. So here it is on the right. Let's cool down the black hole. What the important thing to see, and you could do this for an explicit calculation, is that the mass above extremality as a function of the temperature doesn't behave linearly like the area of the black hole, but instead behaves quadratically. So the mass goes like t squared. Well, why is that a problem? Let's think about it a little bit. Well, suppose that for such a black hole, I look at one mode that it emits, a single quantum of radiation that the black hole emits. I just told you that the flux that the radiation has, it's universal. It's a perfect black body. The radiation has a perfect black body spectrum. And therefore, a single quantum of radiation, it's called Hawking radiation, it behaves linearly in the temperature of the black hole. Which means, from early algebra, at some point, the entropy of the radiation that the black hole emits will exceed the energy that the black hole has above extremality. Now, this means that if I emit a single mode, a single quantum, a single particle away from the black hole, then the black hole, due to energy conservation, the new mass of the black hole will go below this extremal bound, which means that the temperature of the black hole technically becomes negative. Even worse, if you look at in general relativity, what would actually happen is that the solution that you would get that has a mass lower than its charge is actually a singular solution without any event horizon. We would see a naked singularity in our own universe. And that would be extremely bad. So the emission of even a single neutral particle takes the black hole below extremality and causes a complete breakdown of black hole thermodynamics. And the fact that this happened actually hinders our understanding of the evaporation history of black holes, even in theories of gravity like the one in our own universe. So even in general relativity, coupled to the standard model. This brings me to part one of the talk, how quantum gravity corrections actually save the third law of thermodynamics. So what do I mean by quantum gravity corrections? What am I actually talking about? How do we capture the magnitude of quantum gravity corrections? Well, in recent years, we've developed more and more tools to do so, but probably the most impactful tool has been the gravitational path integral. You guys probably have heard of ordinary path integrals in quantum mechanics, in which you sum over all possible paths that a particle can take. We can repeat that process for a theory of gravity in which instead of summing over all paths that a particle can take, we can sum over all possible geometries of space and time and all possible configurations for the particles in our universe. Now, typically, whenever we do a path integral, we have to start by doing some approximation. And this is known as a saddle point approximation. The approximation that you could sometimes do is that if the scale of the action that you're looking at is very large, then this entire integral is dominated by a single term, which is the configuration that actually satisfies the equations of motion. So this is what's called a saddle point. And the solution, the fields the configuration that actually dominates in this path integral is the saddle point that just describes a classical black hole. And if you just take a classical black hole and evaluate the action around that saddle point, you can actually reproduce the entropy formula that I mentioned earlier, since now you have the partition function of the black hole from which you can extract an entropy. Now, in addition to that, the next level of approximation is around this saddle, you want to include fluctuations of all the fields in your theory, including the metric. And this is captured by what's known as a one-loop determinant that captures the fluctuations of all the fields and particles in our universe. So our goal will be to try to compute the next order correction in this formula in as much detail as possible. And for this, we have to look at how the saddle point looks like. This saddle point looks like the cold black hole itself as the temperature becomes lower, which, as I told you, has these spatial slices. and these slices are multiplied by time. So here, each slice here represents, each circle here represents a sphere surrounding the black hole. And combining the radial direction away from the black hole together at time actually gives you another homogeneous space, which is called hyperbolic space. So close to the black hole in this region, the geometry of the space-time itself actually looks very simple. It looks like a sphere times another homogeneous space that actually has negative curvature, a hyperbolic space. Now, around this solution, we can now consider fluctuations for all the fields in our theory. And most fluctuations, like changing the metric a little bit here in hyperbolic space, which is represented by slightly deforming these cows that I put in this image for scale, most fluctuations will be very suppressed. They will have standard deviations that are suppressed in the size of the black hole. And that actually is roughly what happens for most classical systems in our own universe. The reason why quantum fluctuations are not very important when you look at me is because they're suppressed by the number of atoms that I roughly have, or roughly one over my entropy. So most fluctuations are suppressed by 1 over the extremal entropy, which, as I said, for a solar mass black hole scales like 1 over 10 to the 76. So huge suppression. We shouldn't care about those. But in addition to that, what we've discovered is that there is a large set of fluctuations that were missed in the past. And these fluctuations don't scale with the entropy of the black hole, but rather their standard deviation scales with the temperature, or 1 over the temperature. So as the temperature of the black hole goes to 0, if you look at the fluctuation of the action, you will see that the action has modes that are enormously light. And modes that are enormously light have standard deviation that become enormously large, so standard deviations of order 1 over the temperature. So the presence of these modes completely alters the thermodynamics of the black hole. This means that these modes can have very large fluctuations, right? The geometry is not really a classical geometry. So you can see that if you look at the partition function of the black hole as a function of the temperature, as the temperature becomes very small. Here, at leading order, you have Hawking's answer, which tells you that the entropy goes like an exponential in the area. And most modes contribute to this term, which comes from fluctuations, which also, as I said, scales like the entropy to whose standard deviations scale like 1 over the entropy, meaning that the contribution of fluctuations scale like the entropy to some power. But importantly, because of the light modes that now exist in the theory, you have a contribution that looks like temperature to a positive power, which means that as the temperature becomes smaller and smaller, this partition function becomes extremely small. These two terms become completely unimportant. And the only thing that dominates in this partition function is this power law in temperature. So for reference, this power of the area is given by a non-universal correction that depends on the exact number of various fields in our own universe. For the standard model coupled to gravity, this power would be minus 57 over 10. You could just compute it, but regardless of the particle content in our own universe, this power law stays universal. To better understand this power law, let's instead look at that causes these large quantum fluctuations. Let's instead look not at the partition function, but at the density of states, the exponential over the entropy. Here's the old result that Hawking would have gotten by ignoring all quantum gravity fluctuations. Because the entropy goes to a constant as you approach extremality or as you cool down the black hole, the density of states also goes to a constant that is enormously large. It's an exponential of the extremal entropy that I showed you earlier. But once you include the large quantum fluctuations, you see that the density of states gets corrected. And at very small temperatures proportional to exactly the scale at which the semi-classical thermodynamics of the black hole could no longer be trusted, at those scales, the density of states becomes different and becomes enormously small. So large quantum gravity fluctuations can save black hole thermodynamics, making the large degeneracy appearing at extremality fully disappear. So this saves the third law of thermodynamics. And this formula turns out to be completely universal. The density, we can show that the same happens for the density of states, regardless of what kind of space-time we put the black hole in. We could put it in a space with negative cosmological constant or positive cosmological constant, like in our own universe, you'll see the same effect. The same happens regardless of how the black hole is charged. It could be charged under electromagnetism, or it could be charged under the non-abelian fields in our own universe. And it also happens for black holes with any angular momentum. Now, just as a caveat, here I'm showing you the density of states as a function of energy with different values of black hole angular momentum. Now, notice that there's a funny thing, which is classically the angular momentum parameter of a black hole is a continuous number that I tune to whatever I want. Here, somehow I'm plotting half-integer values of angular momentum. What happens is that the sum over all space-time geometries actually says that close to extremality, the angular momentum itself is quantized. And while initially we were only able to derive this close to extremality, we're now able to derive this for arbitrary black holes. We can prove that angular momentum is generally quantized by showing that for each black hole solution that we know in our own universe, there's an infinite other class of solutions that behave the same when you look at the black hole, behave the same far away from the black hole. So they have the same boundary conditions, for which if you sum up over all the space-times that satisfy these boundary conditions, you can show that the angular momentum becomes an integer or half integer. And this has worked with people in the audience. If you're interested, ask John, who's an undergrad here. Okay, so the sum over space-times thus saves the third law of thermodynamics and can even quantize the spin of black holes. Can the same quantum gravity effects save a black hole from going below extremality due to the emission of a single Hawking quantum? And if so, how do such effects change the spectrum of Hawking radiation and the dynamics of black holes in our own universe? And this brings me to part 2 of my talk, how quantum gravity corrections save black holes from going below extremality and make the life story of an isolated black hole completely wild. So it turns out that the same path integral tool that we used earlier to compute the partition function and entropy of a black hole can actually be used to compute more complicated observables. Specifically, by summing over all geometries, we actually have the technology to compute individual matrix elements for the various fields that Hawking radiation can be emitted in. So by matrix elements, I literally mean that we could start out with a black hole with any energy and angular momentum, think about the emission of a single mode that I represent here by an operator, and see what the overlap of this state is with a final state of a black hole that can have a completely different energy. And these matrix elements actually include everything. They include quantum gravity fluctuations, as well as the way in which the fields can back react on the metric, how the field that is emitted can change the geometry of space and time. And using these matrix elements, you could actually find the emission spectrum of Hawking radiation in a very similar way to how you find emission spectra of atoms. Namely, you just couple an atom to the field that you're interested in emitting and apply Fermi golden rule, right? Fermi's golden rule to compute the decay rate or possible emission channels for that atom. Now, For a very cold black hole, it turns out that this approximation where you apply Fermi's golden rule is extremely reliable. And this is because the emission of every single particle is very suppressed by the size of the black hole. It's suppressed by 1 over the charge of the black hole to some power that depends exactly whether we're looking at a scalar, photon, or graviton. But it's always a 1 over the size of the black hole. And if the black hole is very large, the emission is very suppressed. So just to show you what you get if you incorporate these quantum gravity corrections, here is the answer for the flux that the black hole, the radiation flux that a black hole emits in a theory of a universe that would have one massless scalar field. This is not our own universe, since our universe does not have a massless scalar, but it's a good toy model. If we start out with a black hole whose initial energy is very far from the extremal energy, if it's 100 times the breakdown, 100 times the energy at which thermodynamics breaks down, then the flux in which we incorporate quantum corrections is approximately the same as the semi-classical flux. Both fluxes basically look like black body radiation. On the other hand, as we approach extremality, if we look at black holes whose initial energy is very, very close to the extremality bound, so this would be a very, very cold black hole, we see that the quantum corrected flux is completely different than the semi-classical approximation that Hawking predicted. There's an important feature that you could see here. The semi-classical spectrum, since it's thermal, has an arbitrarily large tails. There's always a probability that you emit a mode with very large frequency. Whereas here, if you include the back reaction and quantum gravity corrections of the emitted field on the black hole geometry, the flux is completely cut off at a frequency that's exactly equal to the energy that the black hole has above extremality. So this basically saves the black hole from going below extremality because there are no modes with large enough frequency to take it there. So in other words, this saves, this resolves the paradox that I posed at the beginning of the talk. Now, you might complain a little bit. You might say, well, you're using a toy model that has a massless scalar field. What happens in our own universe? And it turns out that that question is not quite a technicality. It's actually very interesting. So our universe does not have a known massless scalar field, but instead the black hole can emit photons and gravitons. And the difference between a massless scalar and a photon and graviton is that a photon and graviton carry spin. So we cannot ignore the angular momentum of the black hole when studying the emissions of photons and gravitons. And this is because the density of states that a black hole has sensitively depends on the angular momentum that it could have. So here is just a plot where the density of states is non-zero, the area, the values of the energies, where the density of densities of states are non-zero in each angular momentum sector. And when you look at the emission of photons or gravitons, you now have to worry about angular momentum selection rules, just like in atomic physics. And as we approach the ground state of the black hole, these selection rules become more and more important. And this is because quantum gravity effects could be very large in one emission channel and become smaller as the resulting state of the black hole has smaller and smaller angular momentum. And there's an extreme scenario that actually you'll see it can happen in nature. The most extreme version of this phenomenon occurs at the lowest possible temperatures. Suppose that your black hole emits radiation and eventually ends up with an energy that's right here, for which there are no states that carry angular momentum that have a higher energy, right? Well, the angular momentum selection rules tell us that if we emit any spinning particles, we should end up in a sector that carries angular momentum. But since there are no states that carry angular momentum that have a lower energy, we get a problem. It's impossible to emit even a single photon or graviton. So it seems like the black hole evaporation completely stops. Once, not when you reach zero temperature, but rather when you reach a temperature that's small enough that there are no other energy levels that you could transition to. Now, for those of you that are familiar with atomic physics, you've probably encountered this situation before. In atomic physics, this is called a forbidden transition. And an example of this forbidden transition is the 2s to 1s transition of hydrogen. And what happens in hydrogen, it's the same. You end up in a sector in the 2s level. The 2s level is the lowest orbital 2 energy level. You cannot transition to, you have to transition to 1s. But because the emission because the transition is due to the emission of a photon that carries spin, this emission is impossible at leading order. What is instead possible is if you emit two photons or two gravitons at once that are entangled in a singlet state, this transition becomes possible because now you're obeying the conservation of angular momentum. So the conclusion from this analysis is the dominant channel of emission for a very cold black hole is not the emission of a single photon or graviton, but rather the emission of these pairs. Now, when you emit pairs, the total emission rate is extremely suppressed. Remember I mentioned Fermi's golden rule that you might have learned about in your second quantum mechanics class? Well, if you cannot emit a single photon, this means that you have to go to second order in perturbation theory and Fermi's golden rule, which makes the emission very suppressed in the size of the black hole. This power 1 over q to the 32 is way larger than anything that we encountered for a single particle emission. Now, to complete the story about how black holes behave in our own universe, I should mention that our universe doesn't only have neutral particles. It, of course, also has charged particles. And these charged particles can have a drastically different effect on the black hole. So neutral particles never make the black hole lose any angular momentum, right? Any angular momentum or charge. Any charge. So because the extremal bound is fixed as a function of the charge, and it's at the minimum value of the mass, the emission of neutral particles just drives black holes towards extremality, towards this line where the temperature becomes smaller and smaller. On the other hand, the charged particles that are emitted by the black hole, such as electrons and positrons, can make the black hole lose charge. And it can actually drive the black hole slightly away from extremality. You might wonder why I drew the arrow, a little bit below 45 degrees. If you look at the mass and charge of an electron in our own universe, you can actually see that the emission of because the electron has a very small mass compared to its charge measured in Planck units, you could actually see that the emission of electrons and positrons slightly drives the black hole away from extremality. Now, with all this, understanding how charged particles get emitted, we can actually derive the evaporation history of a black hole when left in isolation in our own universe. So suppose that we start at some location in this plane that has black holes at fixed mass and fixed charge. And suppose we start with a black hole that has angular momentum 0. Angular momentum doesn't turn out to be that important in this story unless we get very close to extremality. Well, in this plot, as I said, neutral particles drives the black hole towards extremality and charged particles drive it away from extremality. What turns out to happen is that if the black hole has a sufficiently large charge, namely bigger than 10 to the 44 coulombs, the emission of charged particles is exponentially suppressed. Which means that if you're far away from extremality, the only thing you're emitting are neutral particles. If you're below 10 to the 44 coulombs, what turns out to happen is that the emission of charged particles and neutral particles is roughly comparable. And instead of getting very close to extremality, you eventually will lose sufficient charge that your black hole will be well approximated by an ordinary Schwarzschild black hole. in our own universe. Just for reference, this 10 to the 44 coulombs roughly corresponds to a black hole that has a mass bigger than 10 to the 6 solar masses. So as you approach extremality, we can get in a regime where quantum gravity effects become extremely important, as we just saw. So let's zoom in this area where quantum gravity effects become important. Well, what happens initially is that the black hole emits neutral radiation, photons and gravitons roughly equally, until it reaches an energy scale above extremality, that's the breakdown scale. At that point, single photon or graviton emission is impossible, and you have to emit pairs. That's when the radiation, the rate of the way in which the black hole loses mass as a function of time becomes extremely slow, right? Because the emission of the diphoton emission is a very suppressed process. Now, occasionally, very, very rarely, because this is an exponentially unlikely event, the black hole will emit a single electron or a single positron. And that will drive the black hole slightly away from extremality, from here to here. At that point, what will happen is that the black hole, instead of being a bosonic black hole, if we started out with a bosonic black hole, the black hole will now become a fermionic black hole. And that's because in our own universe, electrons and positrons carry spin half and are therefore fermionic. And by conservation of angular momentum, the black hole itself becomes fermionic. So the black hole will continue emitting photons and gravitons all the way to the breakdown scale. And eventually, when quantum gravity effects become important, notice that the evaporation rate actually is not that slow anymore in an era where the black hole is fermionic. Anyone have any idea why? Okay, if not, this is because if a black hole is fermionic, one photon emission is actually possible. And this is due to the simple selection rule that you learn in quantum mechanics. If you start out with a black hole with angular momentum half, and you emit a photon, you could still end up in a black hole with angular momentum half. So fermionic, the eras in which the black holes are fermionic can actually drive the black hole even closer to extremality. But eventually will again emit an electron, the black hole will become bosonic, and the process will repeat itself over and over again with these hugely spaced out times. It's a tick-tock between bosonic and fermionic black hole eras. Now, eventually what will happen is that the black hole will end up with a charge that's comparable to 10 to the 44 coulombs, or a mass that's comparable to 10 to the 6 solar masses. And at that point, the evaporation into charged particles will no longer be exponentially suppressed, and that will drive the black hole slightly away from extremality, and we'll end up with a Schwarzschild black hole very close to the final regime of evaporation. So a large charged black hole left in isolation is driven towards the regime where quantum gravity effects are critical. And moreover, the black hole in this regime actually explores this regime for the majority of its history, for the vast majority of its history. So if you leave a black hole in isolation, for most of its lifetime, quantum gravity effects will drive its dynamics. And this brings me to part 3 of the talk, how the gravitational path integral sees a discrete spectrum. So far, all the densities of states that I showed you are continuous, and at extremality, we found that the density of states completely disappears. And at first sight, all these results actually are in tension with some of the most famous results in string theory. So most of you probably don't know of this result in string theory, but one of the main claims of string theory is that it could actually count the entropy of certain black holes by looking at a number of string configurations. So by looking at a number of string configuration, you could obtain something proportional to the area over 4g Newton. Now, all the black holes for which string theory does this are exactly the extremal black holes that we study. So all the string theory results do suggest that the entropy of black holes should be extremely large at very low temperatures. So why is the entropy of zero temperature black holes finite in string theory? Well, it turns out that the low energy theories that govern string theories are not ordinary theories of gravity, like gravity coupled to the standard model in our own universe. Instead, they're theories that exhibit symmetry known as supersymmetry, in which every bosonic particle has a fermionic partner. So these are called theories of supergravity. So the graviton itself, the particle with spin 2, has a superpartner that's known as the gravitino. Now, classically, the presence of all these fermionic particles in the universe is not very important. Extremal black holes in supergravity and the extremal black holes in our own universe look almost identical when it comes to just looking at the solutions of the metric. What is completely different, and this was something that was underappreciated for a very long time, is that the fluctuations of space and time itself looks completely different once you take into account these fermionic particles. So previously, I told you that the metric itself, the fluctuations of space and times, there are modes of the metric that have very large standard deviations. Because the metric now, or the gravitino now has a superpartner, the graviton now has a superpartner, which is the gravitino, there are modes of the gravitino that become very, very light and also have a very large standard deviations. So if you really want to account for the fluctuations in this universe, in the universe that string theory governs, you should take into account both fluctuations of the metric and fluctuations of the gravitino. And this completely alters the low temperature behavior of the black hole. So this is how the density of states now looks like if you take into account fluctuations of these fermionic particles. Instead of it being continuous, what you see is that the spectrum, the density of states that includes the quantum corrections for the graviton and gravitino, goes to 0 at an energy that's above extremality. Then there's a gap in the spectrum of black holes, followed by a large degeneracy exactly at extremality, which is exactly agreeing with what string theory predicts. And this actually matches a long-time conjecture for a gap in the black hole spectrum in string theory that was proposed by Maldacena, Strominger, and Susskind. And it was a qualitative conjecture. It didn't have a proof. But now with the path integral, we could actually show that the spectrum of black holes is gapped. And this gap and the large degeneracy that we see on one edge of the gap tells us that we can actually see a sign of a discrete Hilbert space just by summing over all space-times. And the fact that the spectrum is gapped now has non-trivial consequences. So as before, we can try to include these quantum gravity effects to look at how the spectrum of Hawking radiation looks like at very low temperatures. And what you now find is that there are transitions that are possible from a non-extremal black hole that has non-zero energy directly all the way to extremality. But there's nothing in between. It's impossible to transition from this state to a state in between extremality and the level of the gap. So this means that with these black holes, we could actually see the first emission lines for black holes, just like we see the emission lines in ordinary atoms. And if you're interested in this, ask Gwanda, who's a grad student here, for more. Can we do even better? So we've shown that the black hole now has a large degeneracy at extremality. But if I just do a calculation that includes perturbative effects around the black hole background, you can actually compute this degeneracy. It depends on the area of the black hole. And you would find that this degeneracy is not actually an integer. Well, if this path integral is truly describing an ordinary black holes as is truly capturing the states of the black holes, we should really find that this degeneracy is integer. So can we actually show that? And it turns out that the magic of this supersymmetric theory allows us to show that very precisely. So In principle, when we're doing a path integral, we're looking at the action of a theory as a function of all the fields and the metric. Here's like what it looks like pictorially. It's just some complicated landscape, and we're just supposed to sum over all possible configurations and account for e to the minus action. That's very hard because here all these integrals are path integrals. They're actually infinite dimensional, in integrals in infinite dimensional space. So in practice, no one can actually evaluate this. But what you can do in these very supersymmetric, in these supersymmetric theories is you can deform the theory slightly without actually changing the answer. So it turns out that to the action of these theories, you could add a parameter to the action. I won't go into the details of this parameter, but you could add this parameter with an arbitrary coefficient. And whatever the coefficient is, it doesn't really matter for what the black hole partition function is, ultimately. So suppose that we start tuning this parameter to be larger and larger. What turns out to happen in the landscape of possible field configurations is that the action grows and grows all the way to extremely large values as this parameter lambda becomes larger and larger, everywhere except at the locations where this deformation is exactly 0. Now, it turns out that the set of deformation, the set of directions in parameter space for which this deformation is equal to 0 actually has a very small dimension. It's like 5 in this theory of gravity coupled to fermions. So the remaining integral that we have to do is no longer infinite dimensional. It's an ordinary 5-dimensional integral that you could actually do on a computer. So what happens if you do this integral around the black hole background? Well, you get a very nice answer. You get that the partition function of a black hole is a function of this parameter delta that captures the black hole charges. It's just a Bessel function of pi times the square root of the charges. It looks kind of strange, right? Well, you could try to evaluate this answer. Let's say that the charge of the black hole is 200. You would get that the partition function of the black hole is this ugly number. The important thing is not the number itself, is that there's a dot, right? It's not an integer. This number is not an integer. So we seemingly failed. We did an exact computation, and we didn't get an integer yet. Well, what turns out to happen is that the black hole, there are again multiple space-times that look the same far away from the black hole, but have a completely different behavior close to the horizon. These space-times have slightly different topology, and if we really want to study the partition function of the black hole, we really have to sum over all these space-times with different topologies. They roughly look like this. So if you account for the exact answer with these other topologies, you again get Bessel functions times some other complicated functions known as Kloosterman functions. They're functions that are defined in Mathematica. So you could actually plug in this formula at home, see what it gets, see what you get. But I'll do that for you here for a black hole with charge 200. So you have the initial contribution of the black hole, which is this very, very ugly number. Then there's the contribution of the first black hole with a different topology. It gives a contribution that's roughly like 13.42. There are contributions of black holes with topologies that are with spacetimes that are more and more deformed. The more the spacetime is deformed, the smaller the contribution. And notice something, as we're summing more and more terms, we get closer and closer to an integer answer. So eventually, you can show that if you resum all the terms in the expansion, you get an exact integer which exactly agrees with the answer that people obtain in the past in string theory. But this is just by literally doing a sum over all spacetimes and fields. No strings here. So the answer quickly converges, and the entropy of the black hole always gives the logarithm of an integer. Now, the miraculous resummation to an integer that I just showed actually has a name. It's called the Hardy-Ramanujan-Rademacher expansion. It was discovered in the early 20th century. And it's this formula. Ramanujan and Rademacher actually realized that the Bessel functions are a good approximation for a specific set of integers that count the number of partitions of n. And then Rademacher showed that you could improve this approximation by adding further and further terms, and eventually you obtain an exact integer. Now, lucky enough for me in a colloquium, this formula actually has a movie to back it up. So if you're interested, there's this movie, The Man Who Knew Infinity, which is actually kind of about this formula. So I highly encourage you. The movie is actually quite good. It's with Dev Patel and Jeremy Irons, which I love. So I encourage you to watch it at home. Great. Now, for Ramanujan, who actually guessed a lot of these terms, these were just better approximations for the number of partitions. For us, these terms come for more and more black hole spacetimes that resum to the integer that comes from string theory. Now, remember that I told you that there was this regime where we couldn't have any control over what happened, the regime of very tiny black holes. Right, when the entropy of the black hole was order 1 and the temperature of the black hole reached the Planck scale. Well, now we do. We could actually obtain the exact entropy of the black hole for arbitrary charges. And in particular, we could obtain what the entropy of the black hole is, even close to charge equal 1, in which case the entropy of a black hole turns out to be exactly 1. So this formula allows us to probe anything between Planck-sized black holes and large black holes. So to end, let's come full circle. What about the non-supersymmetric black holes, the ordinary black holes like those in our own universe? We looked at their density of states, but what happens if we zoom in very, very close to 0 temperatures? Well, if you think a little bit about it, the perturbative effects that I talked about in the beginning of the talk actually give you an answer that is a bit suspicious. So there is a small mistake that I made at the beginning of the talk that make these black holes not completely resolve the third law of thermodynamics. If you zoom on the density of states at very low energies, you find that the exponential of the entropy goes to 0 as the energy goes to 0, instead of the entropy itself going to 0 as the energy goes to 0. This is wildly different, right? The fact that an exponential goes to 0 means that the entropy actually goes to minus infinity instead of going to 0. So it's a wildly incorrect result. Now, as with the integers, what you can do is we can sum over all space-times to again find the entropy. Not only study the perturbative fluctuations of a black hole space-time, but also understand what possible non-perturbative effects we should include to correctly compute the entropy. Now, it turns out that to compute the entropy is actually quite complicated in this low temperature regime. We can instead compute an alternative quantity known as a second Renyi entropy. And the reason why it's worth studying the second Renyi entropy instead of the ordinary entropy is because if you show that the second Renyi entropy goes to 0, that's sufficient to show that the entropy itself goes to 0. Now, with the second Renyi entropy, what we can do is actually sum over all possible spacetimes that could affect the entropy. And in the low temperature regimes, what turns out to beautifully happen is not only does a single black hole geometry compute to the entropy, but also geometries with slightly different topology. Now, there's a miraculous resummation happening again, which is that if you resum all the possible terms with all different topologies, what we again find is that the entropy of the black hole now goes to the logarithm of 1, which is exactly 0, as beta goes to infinity. And we thus find that ordinary black holes have an isolated non-degenerate ground state, as you would expect from basic quantum mechanics arguments for a system that doesn't have a symmetry that protects that ground state. So let me summarize. The take-home message that you should take home is that the extremal black hole solutions we learn about in our GR classes aren't actually good classical solutions. Rather, quantum gravity effects completely change the geometry of space and time, and even the simplest observables in this geometry. So for instance, the entropy or density of states of the black hole is completely modified when the black hole is cold. The emission spectrum of the black hole is completely modified as the black hole approaches extremality. And in certain theories, including in certain theories, as you zoom towards lower and lower energies, you can actually see a discrete spectrum of black hole states and actually compute the degeneracy of states in a given sector. Exactly. Now, the tool of the gravitational path integral turns out to be very universal. And what we can use it for next is not only to understand black holes, but also to understand when quantum gravity effects are important in other settings. So right now we're actually looking at when quantum gravity effects are critical in cosmology. And if you're interested in that, please ask me after the talk. Thank you very much, and sorry for the small delay.
Okay, thank you, Luca. So it's open for questions. So I'll ask the question you asked. What are the effects of cosmology?
Well, we don't know yet, but seemingly the answer that you get when you include the sum over all topologies is very suspicious. That you get that the similar to how we counted the entropy of the black holes, you could ask what the total possible number of states is in a cosmological space-time that whose spatial slices are closed universes. That's kind of similar, or potentially could represent our own cosmology. And the answer that you get is that the Hilbert space in that case is one-dimensional. And that doesn't make sense with any of the quantum mechanical predictions that we have. Like in a one-dimensional Hilbert space, there are no commuting operators, for instance. So one big question that we've been trying to ask in the past couple of years is, how do we go around that? How do we correct the predictions that we have in a closed universe to make them agree with what we get even in the simplest experiments? And what turns out to happen is that if you instead look at what happens in a closed universe from the inside, rather than asking what the dimension is from the outside. So what happens if you actually do observations in a closed universe, rather than studying the hypothetical Hilbert space from the outside, is that the apparent Hilbert space seen by someone from the inside is much, much larger. It's exponentially larger in 1 over g Newton. And more than that, that allows you, the framework that we're trying to develop allows you to kind of quantify when, not only, what the dimension of the Hilbert space is, but whether there are settings in which quantum gravity effects are important. Right now, a setting in which we believe there are important, that is connected to the black hole setting that I talked about, is in the black hole interior. We kind of have calculations that suggest that if you jump in a black hole interior, the interior itself might not be described correctly described by general relativity if the black hole is sufficiently old, like very old, exponentially old. But we don't yet have concrete predictions for cosmology yet. But it's kind of an exciting avenue because this framework, while initially it gives you a wildly incorrect answer, the answer is so wildly incorrect that it makes it kind of interesting and easy to find new effects that were missed in the past.
Anyone else have questions?
What is the ultimate fate of a very tiny evaporating black hole?
Oh, so we don't know. So maybe I should have specified. We can correctly predict in this plot, we can correctly predict the evaporation history of a black hole all the way up to a tiny scale here when the black hole becomes Planck-sized and has finite temperature. It's not an extremal black hole, like the one we discussed in supergravity. We don't know what happens in that regime because we're still using, a theory that's just Einstein gravity coupled to the particles that we know in our own universe. As you reach smaller and smaller black holes, the temperature grows. And eventually you'll reach temperatures of order the Planck scale. So, you'll really need to understand your theory up to a very, very large cutoff, which we don't know. So we understand everything in this plot except the very, very final moments of a black hole. Like, you could trust this plot probably until the black hole is like 1,000 Planck sized. After that, I give no guarantees.
Could you explain again? You mentioned that data goes to infinity and
Mm-hmm.
Could you explain that?
Yeah, so this is what you would.
Repeat the question.
Oh, could you explain why, as beta goes to infinity, the entropy went to 0? So maybe I went a little bit fast around that. You're referring to. This calculation resums to give you an entropy that's log 1. Yeah, so it's very non-trivial to see why this calculation works. It requires there to be, the ratio between geometries that look wildly different and have different topology. It requires that this ratio goes exactly to 1 as the temperature goes to infinity, and that's actually something that is very hard to see. In fact, the way in which we saw it is because mathematicians studied the space of surfaces in the past, and they produced very interesting work that gave us the capability to resum all the terms in this expansion. So the fact that it goes to 0 is very complicated to see from the geometry of space-time, the sum over space-times. What is easy to kind of intuitively see is that this is the answer that you should get, because you have a quantum system that doesn't have any symmetries, right? So you should expect that if you study the energy levels of that quantum system, you won't have any surprises. You won't have any surprise degeneracies. And if you don't have any surprise degeneracies, then the entropy should just be dominated by the lowest state in the system as the temperature goes to 0, right? And if there is a non-degenerate lowest state, then this is the answer that you should get. The miracle is that we're able to reproduce this from a sum over space-times. I should have mentioned this, the sum over space-times we could do exactly not in a full theory of quantum gravity like in our own universe. We can do it in a theory where we kind of neglect some of the degrees of freedom in our own universe. That's why we're able to do it exactly.
You have a well-defined temperature throughout all this, it seems like, but if there's really violent things that happen with black holes, do they ever go out of equilibrium so the temperature's not well-defined? Do you have a notion of the thermalization time?
Oh, yes. There's a notion of the thermalization time. Yeah. People study black holes out of equilibrium. It just here, the easiest problem is to study a black hole in isolation. If you study, a process that involves a black hole and maybe a star falling into it, you could ask, eventually a new black hole with a slightly bigger mass will form, and eventually that black hole will thermalize after the thermalization time. But you could ask what happens in the meantime. Are quantum gravity effects important? We haven't studied that. In fact, an interesting question would be to analyze what happens if something falls in an extremal black hole. Something large that can, put the black hole out of equilibrium with an initial state in which the space-time is highly fluctuating.
Okay. Can you motivate in a simple way why the electric charge makes it cold?
Why the electric charge makes it cold? Yeah, so the electric charge by itself does not make it cold, as in throwing an electron into a black hole doesn't necessarily make it colder. but rather, what happens is that a black hole with a charge can get arbitrarily cold. Yeah. I'm not sure I have a good intuitive picture for why having a charge allows you to do that, but yeah, mathematically, it's that's kind of easy to see.
Okay, well, let's thank our speaker again.